Welcome to the session on vectors, 3D coordinates and vectors in 3D. The objectives for this session are to understand 3D Cartesian coordinates and use vectors in 3 dimensions. In 3 dimensions, Cartesian coordinates are sometimes called x, y, and z axes. Coordinates of a point in 3 dimensions are written as x, y, z, or vertically x, y, z as shown here. We can also represent these on a diagram with the x, y and z axes as shown intersecting at 0 or the origin at right angles. The point 1, 0, 0 appears on the x-axis here, and the point 0, 5, 0 appears on the y-axis here, and the point 0, 0, 3 appears on the z-axis here. Let's try visualizing a more complex coordinate, a equals 2, 3, minus 1. Here's the point 2 on the x-axis, the point 3 on the y-axis, and the point minus 1 on the z-axis. If we put all of these together, we can visualize A, which is positioned as shown. So essentially, if you want to visualize this, think of the x and y-axis as being drawn on a flat surface, and the z-axis is either rising above the surface or below, depending on the z-coordinate. We can now also find the distance from the origin, or the length of this vector, A, and we can use Pythagoras' theorem to do that. The same principles apply, so we have that the distance from the origin to the point x, y, z is root of x squared plus y squared plus z squared. The unit vector is a hat, which equals a over mod a, which is the length of the vector of a. Let's take a look at an example. We are required to find the distance from the origin to the point a equals 2, 3, minus 1, and hence find the unit vector a hat. So mod a equals 2 squared plus 3 squared plus minus 1 squared, all square rooted, and this equals square root of 4 plus 9 plus 1. And this equals root 14. So mod a equals root 14. A hat equals a over mod a. So we have that a hat equals 2, 3, minus 1 over root 14. If we want to find the distance between 2 points, x1, y1, z1, and x2, y2, z2, then this is given by the formula shown on your screen. Let's apply this formula to an example. We are required to find the distance between the points A, 1, 3, 4, and B, 2, 5, minus 1 to 1 decimal place. Let's try visualizing this first, although we don't have to once we become more adept at doing these types of questions. So here's, for example, A, and here's the point B, and we're required to find this length here. So we apply our formula, mod AB equals the square root of 1 minus 2 squared plus 3 minus 5 squared plus 4 minus 1 squared. And this is equal to square root of minus 1 squared plus minus 2 squared plus 5 squared, which equals square root of 1 plus 4 plus 25, which equals square root of 30. And this equals 5.5. Position and displacement relative to the x, y, and z axes can be described using 3D vectors. Unit vectors I, j, and k along the x, y, and z axes are denoted by I equals 1, 0, 0, j equals 0, 1, 0, and k equals 0, 0, 1. So for any 3D vector, pi plus qj plus rk equals pqr vertically, as shown. You can now see the I, j, and k vectors on the x, y, z axes. Here's 1, 0, 0, or I, here's j, and here's k. Three-D vector addition and multiplication use the same principles as 2D vector addition and multiplication. A vector can be described using its displacement relative to the x, y, and z axes. Multiplying a vector by a scalar, we have lambda times pqr equals lambda p, lambda q, lambda r. Adding two column vectors gives us x1, y1, z1 plus x2, y2, z2 equals x1 plus x2, y1 plus y2, and z1 plus z2, as shown here. The position vector of a point is the vector from the origin to that point, such as this one. So here we have the position vector 0p or OP, and the position vector is 2, 3, minus 2. Let's take a look at another example. Consider the points A, 2, 3, minus 2, and B, 1, 1, 4. We are required to find the vector AB in IJK notation. So visually, we have the position vector A as shown and the position vector B as shown. So here's OA and here's OB. And we're required to find AB. Now AB equals OB minus OA. And so we can now carry out this subtraction. Here's OB and here's OA. And therefore AB equals 1 minus 2, 1 minus 3, and 4 minus 2, which equals minus 1 minus 2, 6. In IJK notation, this is represented by minus I, minus 2j, plus 6k. Now let's take a look at parallel vectors. Two vectors A and B are parallel if A equals lambda b for some scalar lambda. Let's now take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve part A first. Two vectors A and B are given by A equals 4i plus 2k and B equals 6i plus 4j minus 3k. We are required to find A plus 2b and 3a minus 4b. So let's solve this. Vertically, we can write A as 4, 0, 2 and B as 6, 4, minus 3. This implies that A plus 2b can be written like this. And so we have that a plus 2b equals 4 plus 12, 0 plus 8, and 2 minus 6, which equals 16, 8 minus 4. Similarly, we can find 3a minus 4b. And so we have that 3a minus 4b equals minus 12, then minus 16, then 18. Now let's have a go at part B. We are required to state with a reason whether each of the vectors in part A is parallel to 4i plus 2j minus 1k. So let's solve this. Here are the two vectors from part A. In order to see if either of these is parallel to 4i plus 2j minus 1k, factorize so that the x component is 4, and then compare the y and z components. So let's do this for the vector a plus 2b. We're going to factor so that a plus 2b has x component 4. And this can be done by taking out 4, as shown here. Now let's compare the y and z components. We can see that a plus 2b is a multiple of 4i plus 2j minus 1k, and therefore a plus 2b is parallel to this vector. Now let's do likewise for 3a minus 4b. We're going to make the x component 4, or factorize in such a way that the x component is 4. So minus 12 equals minus 3 times 4, as shown here. Now let's compare the y and z components. Notice that they do not correspond to 2j minus 1k. And therefore, from the definition, we can see that 3a minus 4b is not parallel to 4i plus 2j minus 1k. Now let's look at finding angles. Suppose we have the vector a equals xyz, making an angle theta x with the positive x-axis. If we visualize it, it will look something like this. So we have that cos theta x equals x over mod a. Similarly, we can define cos theta y and cos theta z for angles theta y and theta z. Let's take a look at an example. If a equals 2, 3, 5, then we have that mod a equals, from Pythagoras, 2 squared plus 3 squared plus 5 squared, all square rooted, which equals square root of 34. So if we want to find cos theta x, we have that cos theta x equals 2 over root 34, which equals 0.342997. And therefore, theta x equals 69.9 degrees. This brings us to the end of this session. If you have understood its contents, you should be able to understand 3D Cartesian coordinates and use vectors in 3 dimensions. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.